Hello everyone, let's talk about the uh, Advanced Structural Dynamic Term Project. Firstly, let's start from the system identification technicals. The field of system identification use statistical methods to build mathematical models of dynamic system from measured data. System identification also includes the optimal design of experiments for efficiently generating informative data for fitting such models as well as model reduction. For linear systems and models, the interplay between time and frequency domain methods is well known and much utilized in, for example, control design. Indeed, the duality is a cornerstone in many design and analyze methods. For linear system identification, the links between time and frequency domain methods are equally important. However, the tools have traditionally not been quite integrated. Of course, methods to directly estimate frequency response from time domain data through various subtle analysis techniques are classical. At the same time, one can distinguish one community that basically work with data in the time domain and primarily estimates parametric time domain models and all constantly complexments that with spectacle analyze. Another community use frequency domain data, periodic inputs, and well-controlled experiments to build model of similar kind transfer function as well as refine frequency function estimates. Secondly, I want to talk about the uh, identification procedures. Identification procedures is composed of 6 main steps. Experiment design, input-output measurements, model structural selection, structure parameter determination, model estimation, model validation. The model-based control design process involves modeling the plant to be controlled, analyzing and synthesizing a controller for the plant, simulating the plant and the controller, and deploying the controller. Choosing a suitable model structure is prerequisite before its estimation. The choice of model structure is based upon understanding of the physics systems. 3 types of model are common in system identification: the black box model, gray box model, and the user-defined model. The black box model assumes that the system are unknown and all model parameters are adjustable without considering the physics background. It can adjust all the parameters arbitrarily. The gray box model assumes that part of the information about the underlying dynamic or some of the physical parameters are known and the model parameters have some constraints. The user-defined model assumes that the commonly used parametric models cannot represent the model it wants to estimate. It can define special system model by using a template with a predefined input-output interface. Next, I want to introduce different system identification techniques. A variety of parametric model structures are valuable to assist in modeling an unknown system. Parametric models describes uh, systems in terms of differential equations and transfer functions. These models provide insight into the system physics and compact model structures. It is often beneficial to test a number of structures to determine the best one. A parametric model structure is known as a black box model, which defines either a continuous time system or a discrete time system. So the black box model uh, uh, generally general or linear model. Generally, it can describe a system using the following step, which is known as the general linear polynomial model or the generally linear model. The general linear model structure provides flexibility for both the system dynamic and so and sto and stochastic dynamics. However, a nonlinear optimization method computes the estimation of the general linear model. This method requires intensive computation with no guarantees of global convergence. Simpler models that are a subset of the general linear model structures are possible. By setting one or more of polynomials equal to 1, it can create these simpler models such as ARX, ARmax, box Jenkins, and output arrow structures. Each of these methods has their own advantage and disadvantage, and is commonly used in real-world application. AR model. The AR model structure is a process model used in the generation of models where output only depends on previous outputs. No system inputs and or disturbance are used in the modeling. This is very simple model that is limited in the class of problems it can solve. Strictly speaking, this means that the AR model structure is the model for signal, not a system. Time series analysis, such as linear prediction coding, commonly use the AR model. Next is ARX model. The ARX model is the simplest model incorporating the stimulus signal. The disadvantage of the ARX model is that distributions are part of the system dynamics. The transfer function of the deterministic part of the system and the transfer function of um, stochastic part of the system have the same set of poles. This coupling can be unrealistic. The system dynamics are the system dynamic and stochastic dynamics of the system do not share the same set of poles all the time. However, it can reduce this disadvantage if it have a good signal to noise ratio. ARX model. Unlike the ARX model, the ARMax model structure includes the disturbance dynamics. ARMax models are useful when it have dominating disturbance that in turn early in the process, such as the input. For example, a wind gust affecting an aircraft is dominating disturbance early in the process. The ARX model has more flexibility in the handling of disturbance modeling than the ARX model. State space model. The Purian's classical parametric system identification method minimize a performance function which is based on the sum of squared errors. These methods work well in many cases. However, for complex systems characterized by being of high order, they can experience many local minima in the performance function and thereby lack a convergence to global minima. The user will need to specify complicated parameterization of system orders and delays. They also may suffer potential problems with numerical instability and excessive computation time to execute the iterative numerical minimization method to be needed. In addition, modern control methods require a state space model of system. For cases such as this, the state space identification method is the appropriate model structure. In general, the state space model provides a more complete representation of the system, especially for a minimal system. Then polynomial models because the state space model is similar to a first principle model. The identification procedure does not involve nonlinear optimization, so the estimation reach a solution regardless of the initial guess. Moreover, the parameter setting for the state space model are simpler than polynomial models. And next is a gray box model. In some circumstances, it has already obtained part of the information about the underlying dynamic or some of the physical parameters of the system. It can select the gray box model to specify these partially known physical parameters or some concentrates. Then it can estimate remaining unknown parameters with partially known model estimation methods. Gray box model identification involves optimization process to minimize the difference between the estimate output and the measured real output. Finding the global optimum depends on the limited range aside and the initial values to decrease the estimation time, it can set a narrow limit range and reasonable initial parameters. The above general linear polynomial polynomial models are commonly used because these models separately describe the deterministic and stochastic parts of a system. However, in classical control engineering, the deterministic part of the system is more important than stochastic part. Transfer function models are commonly used to describe only a deterministic part of the system. Transfer function models can describe both continuous time and discrete time system. Use transfer function model structure to represent a uh, a single input and single output physical systems or multiple input and signal and a single output physical systems. For more complicated multiple input and multiple output physical system, use the state space model structure. For the black box model, determining the delay and the model order for the parametric model is typically a trial and error process. The following is a useful set of steps that can lead to a suitable model. First, obtain useful information about the model order by observing the number of reasons values in medium-size ARX model. Choose the delay that provide the best model fit based on prediction errors or other fit creator creation. Secondly, test various ARX model orders with this delay, choosing those that provide the best fit. Finally, since the ARX model describes both the system dynamic and noise properties using the same set of poles, the resulting model may be unnecessarily high in order. By plotting the zero and plots and looking for the cancellations, you can reduce the model order. The resulting order of the plots and zeros are a good starting the point of for AR Max. With these orders used as model parameters and first or second order models for the noise characteristics. If it cannot obtain a suitable model following these additional physics insight into the problem might be necessary. Compensating for nonlinear sensors or actuators and handling of important physical nonlinearities are often necessary in addition to use a ready-made model. Okay, let's talk about the ARX technical information. The auto regressive with ARX model was designed to represent the system dynamic of actuation process. The estimation of the ARX model is the most efficient of the polynomial estimation methods because it is the result of solving linear regression equations in an analytic form. Moreover, the solution is an unity. Uh, uh, the solution only have one. In other words, the solution always satisfies the global minimum of the loss function. The ARX model, therefore, is preferable, especially when the model order is high. So we can see the process of ARX model structure. Um, auto uh, Since input-output relation is given by the linear difference equation, and then rewriting the in transfer function forms, auto autoregressive part a q y t and and part BQUT. Therefore, this model structure is also indicated as an ARX model, which can be written uh, written in another equation. More specifically, ARX model structures are also denoted as ARX, uh, where the number of sibling intervals related to that time. Next, I want to introduce the model estimation. The unknown parameters of ARX structure were estimated by using linear regression approach by using the concept minimizing the sum of the square residue. The definition of regress is calculate the value of input the value of output at any point in time domain based on the outputs and inputs. It also can be determined by the frequency domain. And in addition, the model validation. The main objective of model validation is to validate the dynamic model and that represents the system response as a real process. The validation was done by using the one part of experimental data that was separated by using interlacing techniques. There are many techniques are applied in model validation, such as one step ahead prediction, residual analysis, coefficient of determination root means a square error and correlation analysis. Okay.
Hi everyone, my name is Rangu and I'm going to introduce the rest part of the lecture. An example is demonstrated in this part. A four-story shear building is idealized into a multi-degree of freedom linear elastic dynamic system. For the first step, the model is analyzed by general response of linear elastic system. Then, by using the output displacement data, the input force function, we can back-calculate the transfer function generated by ARX function in the MATLAB. The conjugate roots and the residual of the transfer function can be further used to compute the model frequency and model shape. Then the mass, stiffness, and damping matrix of the system can be calculated, as well as the comparison of the displacement plot. As we can see from the slides, the four-story shear building is simplified into this system. And in an earthquake activity, the force acting on the system is idealized into a single sinusoidal force on the roof floor. The natural frequency of the earthquake is assumed to be 10 pi radians per second. The peak force of the earthquake that acting on the roof floor is assumed to be 10 kilonewtons. And in order to comply with the calculation of the stiffness and the mass matrix, the mass for each floor is transferred from the kilograms into the kilonewtons second square per meter. And the node in the roof floor is said to be the degree of freedom 1, and the node at the first floor is said to be the degree of freedom 4, and the displacements of these 4 degrees of freedoms are used to calculate the ARX results. The next step is to transfer the stiffness and the mass for each degree of freedom into the system mass and stiffness matrix. The result is given in the slides. Then the next step is to calculate the natural frequency of the building by applying this formula: K minus m times omega n squared times phi equals to 0, where the K is the stiffness of the system and the omega n is the natural frequency we want to find for each mode, and phi is the normalized shape factor for each different mode. Here the results are generated by the MATLAB. The natural frequency and mode shape is listed on the slides as well. The figure shows how each mode is going to move at each degree of freedom. Because for each mode the participation factor is different, so the maximum displacement for each mode is also different. The figure in the slides only shows the shape for each mode, but not to scale. By using the equations of the Rayleigh damping, and we assume the damping ratio for the first story and the roof story is 3%, then the damping ratio for the second and third floor can be calculated. The second degree of freedom is 2.37%, and the third degree of freedom is 2.57%. Then the generalized mass, stiffness, and damping matrix are calculated by applying the transverse normalized shape matrix times the matrix for the mass, damping, and the stiffness times multiplied by the normalized shape factor. The general response of the system can be represented by this equation, and for the first term of this equation represents the transient response of the system. This term, which closely resembles the solution of a damped free vibration and is a function of the system's natural period, is damped out quite quickly. And the second term represents the forced vibration response of the system, and is a function of the force frequency. And in the formula, XST represents for the largest displacement under the peak force during the excitation, and the beta represents for the ratio of the forcing frequency to the damped natural frequency. And the figure on the slides shows the displacement plot for each degree of freedom over the total of 2.5 seconds. The sampling time for each discrete displacement is 0.01 seconds. The figure on the slides shows the displacement for each story. As we can see on the figure, the transient response is quite obvious at the first 1.5 seconds. And after the 1.5 seconds, the steady-state response dominates the displacement. The displacement data for each story will be used to add the output in the ARX function in the MATLAB. The displacement data at different sampling times, such as 0.01 seconds, 0.05 seconds, 0.1 seconds, 0.5 seconds, will be recorded accordingly to compare the accuracy of ARX function in the MATLAB under the different sampling conditions. And the different displacement results and the compare of the result and the discussion will be given in the later slides. And now we are going to apply the ARX system identification technique in this here building. Under this condition, the YT on the slides is defined as the displacement output for the ARX function. We generated these datasets from the previous section. The displacement at each degree of freedom can be used as output, and we will discuss it later. The input xt is defined as the input force. AQ, BQ are the regression parameter for the input and output. ET is defined as the zero mean white noise. And by the definition, since there are 4 degrees of freedoms, so we assume that there will be 4 pairs of conjugate pairs of roots for the ARX transfer function, and the AQ has an order of 8, and the BQ has an order of 9. And in the equation below, there is another form of the transfer function HQ. BQ divided by AQ is equal to this function. And the R key represents for the NA by NA residual matrix, and the KP is defined as the poles of the transfer function. Finally, the HI represents for the ICE model for the system. And based on the credited steel dynamic behavior study, we found the following equation, which is widely applied in the ARX structural dynamic analysis. And from this equation, we recall that the PI is the poles of the transfer function for the ICE mode, and the HI represents for the ICE mode for the system in the transfer function. The function arguments returns the angle between the positive x-axis and the poles pi. The delta t is defined as the time delay. The beta phi I is the mode shape multiplied by the mode participation factor, which means the factor's mode shape. The function Re returns the real part of the given complex number, and the function of sign returns the positivity or negativity of the number. The function Im returns the imaginary part of a complex number. And now we type these functions into the MATLAB after we get the poles of the transfer function that we mentioned previously. And now let's summarize the critical points and the processes for the ARX system identification techniques. Firstly, we got the force, and we got the initial conditions and the displacement time history. Then we type the force and the displacement history into the MATLAB. We use the ARX function in the MATLAB to find the residual, the poles, and the ICE mode of the transfer function. Then we use the value to calculate the frequency, damping, and the damping ratio and the shape factor. We also look into the displacement between the calculated one and the ARX generated one. Then we will compare and back calculate the mass, stiffness, and damping matrix and discuss the results under the different conditions. And here's a pose after we running the program, and for the first figure we can see the pose of the displacement history of U1, which means that we will use the U1 as the output of the function, and for the second figure we use the displacement figure of the degree of freedom of 2 to find the roots, and we see that these two roots are different. And now let's have a look at into the result and discuss the results. The first column shows the result that we generated from the MATLAB. Then we transfer it into the natural frequency in radians per second, and then we compare it into the percentage differences, and we do it in the damping ratio, and we find that there's almost no differences for the ARX calculated one for the natural frequency and the damping ratio. And one interesting thing we found during the modeling process, we find that when we change the displacement history for the degree of freedom 1 into degree of freedom 2 or 3 or 4, the natural frequency that comes out from the ARX function basically don't change. All values are exactly the same. However, the order of the values changed. For example, when the sampling time is set to 0.1 or 0.02, the natural frequency that comes from the MATLAB ARX function are not same ordered. So we can use a new function to get everything in order. However, this is under the condition that there will be only 4 natural frequencies that comes out from the MATLAB. We assume that there are 8 poles, 4 conjugates roots of the transfer function, so we only get 8 poles. And the number of poles divided by 2 is exactly the total number of degree of freedoms. In other words, there are no redundant force or redundant results and extra meaningless results that comes from the function. However, if we don't know the total degree of freedoms in a system, or I don't know which one of the roots is meaningless and which one is useful, we cannot use the ARX function under that condition. And now let's have a look at into the displacement history and the mode shape that is generated by the ARX function. As we can see from the displacement history, the estimated plot, which is calculated by the ARX function, is completely overlapped with the displacement that comes from before, when the sampling time is set to be 0.01 and the total time is set to be 5 seconds. And when we change the sampling time and the total time in the ARX function, the percentage of fitness of the plot will change, and we will discuss later. The 100th fitness of the plot is because since we do not introduce any noise source to the system, so we can kind of get the 100% accurate. And for the mode shape, we found that the result changed every time. When we set the sampling time to greater than 0.05 seconds, the mode shape is completely wrong. And when we higher the order of NA and NB, which is the order of AQ and BQ from the transfer function, we got the wrong mode shape. And the figure in the slides is the most accurate normalized mode shape. And here are the mass, stiffness, and damping matrix. And since we got a pretty inaccurate mode shape, we got some obvious inaccurate elements in the stiffness and damping of the mass matrix. And now let's discuss the parameters that will affect the accuracy of the ARX system identification function. Firstly, I changed the total time and the sampling time in the function, and as we can see from the first table, when we use the larger sampling time, change the sampling time from the 0.01 second to 0.05, 0.1, 0.2, 0. and 0.5 seconds. Generally lower the percentage of fit to plot for the estimated displacement. And when I use the 0.5 sampling time and 10 seconds total time, the MATLAB returns error and there are too many parameters in the transfer function. And besides, when the sampling time is getting larger, we will get worse mode shape, and when the sampling time is greater than 0.2 seconds, the MATLAB will return 0 value for all the mode shapes. And then let's look into the frequency of the system that the MATLAB computed under the different sampling time condition. And when the sampling time is set to be 0.05, the frequency that calculated from the MATLAB seems very accurate and is as accurate as what we got from the sampling time of 0.01. And however, when the sampling time is set to be 0.1 second, the vibration mode with the higher frequency, as we can see on the circle, seems to have a very large percentage of the differences, and I tried several times that I found that when the delay time, the sampling time is getting larger, the mode with the higher frequency will be very sensitive to the sampling time, which means the larger frequency of the mode, the higher percentage of the inaccuracy that we generated from the MATLAB. Our ARX model have pretty high accuracy in the natural frequency of the system and the damping ratio we calculated from the ARX model, and we also got intermediate accuracy of the mode shape. However, there are several limitations of our ARX model that maybe the next time we will make the problems when using this function. For example, we know the number of the degree of freedom in this system, so we can set the NA value to 8 and NB value to 9. But what if we do not know the total number of degree of freedoms, and under that condition, we will increase the value of NA and NB, iterate our model and find a useful roots, and find if we can let the roots converge. This will be a very complicated process. And besides, our model will lower the accuracy when sampling time changed. And when we use the other structural system, we will have to try different value of the sampling time to make sure the accuracy of the results. And the noise term in the ARX function is assumed to be 0 in mean. However, sometimes in the practical application, the mean value of the noise will be varying with time. So in general, our ARX model cannot be a completely black box system identification function. We have to set initial conditions, initial assumptions to get the accurate returns. And finally, there are some general limitations for the ARX system identification technique. As we mentioned before, the noise function is inaccurate in the ARX system. Alternatively, we can use the ARMAX function, which adds one equation term CQ in the front of noise term, so we can manage the noise more precisely. Besides, the structural behavior in earthquake is very critical in the structural monitoring. During an earthquake activity, the building will have nonlinear structural behavior. The seismic resistance member will yielding during the earthquake. And the ARX cannot analyze the nonlinear behavior of the structure. As a result, we can use NLARX instead, or other techniques which can analyze the nonlinear behavior of the structures. And finally, ARX cannot work if the damping of each floor is not proportional to the mass and stiffness of the related story, which means the story is unconventional damping. And these three limitations cannot be solved directly by using the ARX identification techniques. And this is the end of our lecture. Thank you very much.